Okay. Okay, so it is my distinct pleasure to introduce today's speaker, Dr. Professor Jonathan Tan. I'm not really good at titles, but Jonathan obtained his PhD from the University of Berkeley, and then had the first postdoctoral appointment at Princeton as a Spitzer Fellow. Then moved even further east and became a Zwicky Fellow at ETH in Zurich. But he had enough of Europe for a while, so he went back to the States and became a professor at the University of Florida, where he stayed until a few years ago. Then he had too much of the US, so he decided to move back to Europe, and now he's a professor at Chalmers in Sweden. He's a world expert on star formation from the theory side, and especially he's interested in the role of the magnetic field, as I am, and he will be in Raphael's thesis tomorrow. So without further ado, Jonathan, the floor is yours.
Thank you very much. It's a pleasure to be here. My first time in Crete, and Sweden is already cold and wet, so I'm enjoying my time here very much. Yes, and I'm looking forward to the excellent talk we will hear tomorrow. So I am at Chalmers in Gothenburg, Sweden, but I still am a professor in the US. We have a joint appointment at the University of Virginia, where half the research group is, and we run a few programs there. There are different postdoc ads that are about to go out to postdoc, the Origins Fellows, and the Virginia Theoretical Astronomy positions will be advertised this year. And in Sweden are also Origins Fellows, and the Ariel Fellowship to do with the ESA exoplanet mission will be announced soon. If you're an undergraduate, we run a summer program, CASM programs based in Sweden in the summer. And so we take people from all over the world, and if you're teaching undergrads who want research experience, do point them in this direction. Okay, and then this work is in a collaboration with a huge bunch of collaborators, many students and postdocs, many undergraduates as well have been involved. Okay, so let's jump into it. What I'd like to do today is to tell you the latest that we're doing in the field of massive star formation locally, but then in the last third, I'm going to try and go out on a limb and say something speculative about the formation of the first stars and the first, perhaps all, supermassive black holes. So it's all connected by the physics involved in massive star formation. So things, stars greater than 8 times the mass of the sun, at least on the solar conditions here, and expected to end their lives as supernovae. That's traditionally the definition of massive stars. So as we'll see from the very first dark matter mini halos, slowly capturing hydrogen, helium throughout all of galaxy formation evolution, around our own galactic center, there are massive stars, and in star clusters, typically massive stars are found there as well, influencing perhaps the birth of most planetary systems. So they're important everywhere. The physics, of course, gravity is compressing gas, but what pushes back can lend to complexity. So, where do we begin? All of these processes can in some way, develop pressure gradients which prevent a collapse. So it's understanding the balance between these that's challenging. So we'll, as a theorist, we started developing analytic or semi-analytic models for some of these processes. We work to test them with numerical simulations. I'll show some examples. But over time, we start to use more and more telescopes to try and test these predictions. I'll use a little bit of notation, not too much. Self-gravitating gas that could become rounded under its own gravity, that collapses to form a single rotationally supported structure, disk, in its center we'll call a core. Perhaps one star or a little multiple from disk fragmentation could arise. A self-gravitating structure that is fragments into a bunch of cores we'll call a clump, and that will form a star cluster. Many open questions remain after many years. We don't know why a particular region of a giant molecular cloud decides to become unstable. You could imagine two possibilities. The internal pressure support, whether it be magnetic or turbulent, it decays away, and then a region decides to form a star cluster. Or you could imagine external compression that pushes it over the edge, something that was already self-gravitating but stable, pushed over the edge. Perhaps we like cloud collisions, but you could imagine any kind of pressure wave from feedback as well. Then the initial conditions of cores and clumps, one can ask how close they are. Just when the first star is starting to form, how close is it to pressure equilibrium or virial equilibrium, so energy equilibrium between self-gravity and internal energies. And as we'll see then, the answers to those questions can affect the basic accretion mechanism. Are there cores at all masses, or for the most massive systems, is it a more chaotic, competitive accretion process, or even stellar merger process? So core accretion theory developed over a number of decades. Frank Hsu was one of the leaders in this field. This is his classic cartoon. Here are his cores, disk, magnetic fields are threading the disk and a star. So disk winds or X winds or both help remove material and leave behind a remnant system. Now with ALMA, in low mass star formation, one sees beautiful order. These are channel maps in CO. Here's a rotating disk here, but this is just showing you the beautiful symmetric outflow cavity. So one has hope that an analytic theory could help to explain some of this phenomena. Now, for massive star formation, well, when we came into this with Chris McKee, this is 20 years ago now, a bit more than 20 years ago, there was a whole range of possibilities being discussed for accretion rates, how quickly the star is gaining mass. So dm by dt here, you could see papers describing accretion rates 10⁻⁵ solar masses per year. It would take a long time to build up a 100 solar mass star at that rate, up to something like 1% of the solar mass per year accretion rate. So the turbulent core model, which is 20 years old now, basically said that cores fragment from a clump, and the properties of the cores depend on the pressure in the clump. So here's our clump. The pressure is self-gravity. This is Newton's G. This is the mass per unit area squared here. That's the weight of this as an atmosphere, but without any surface, of the self-gravitating gas in the cloud. Phi is just a dimensionless factor of order unity. As we'll see in a moment, the kinds of mass surface densities that are typical in the galaxy are such that the pressures we have here are too high to be supported by thermal pressure if the gas can cool down to order 10 Kelvin. So thermal pressure will have no chance of supporting this thing, if it is going to be supported. So you're left with non-thermal forms of pressure, which can be some form of turbulence or magnetic fields. So although it's called a turbulent core model, it's really the turbulent and/or magnetic field model that's involved here. And we assume essentially equiposition between the components. So as we'll see, a typical value, we'll motivate that in a moment, is about 1 gram per centimeter squared as a typical star-forming environment. So, there will be, we observe that there are turbulent motions in here. Turbulence can compress gas. Locally, things can become unstable. A whole mass spectrum of cores could arise here. That's the proposal. So you have some, all rare, massive starless cores, many more low mass cores, and the condition is that the bounding pressure on this core is this ambient clump pressure. That sets all the properties of the core. So a core of a given mass, if it's going to become unstable, has to reach a certain density, a certain size under these conditions to then undergo collapse. And then that sort of classic cartoon from Frank Hsu is just applied here with a few minor modifications. So you see, it's important to know this bounding pressure will tell you, for example, the accretion rate will be, of order the mass of the core divided by the free fall time of the core, which depends on the density, which will depend on the pressure. So in practice for the experts here, we have essentially singular polytropic spheres, structures for the core, pressure truncated by the ambient clump medium. Now, in the competitive accretion or clump-fed accretion model, which is still active, mainly driven by what's seen in simulations, we have massive stars forming together with many low mass stars and sort of competing for mass in a global cluster potential. The clump is collapsing globally and supplying material to the central region, and it's quite different. That there is no massive prestellar core. The rate at which accretion happens here is actually set by the global collapse of the clump. It's actually much slower. It takes longer to build up a massive star, and a massive star has to form in a cluster. That behavior tends to be seen in many people's simulations. The closest example of a massive protostar is in Orion KL, 400 parsecs away, and it has this weird explosive outflow. It's been known for years, and protostellar mergers are invoked as being responsible for this thing which exploded 500 years ago in some merger which then ejected at the same time some explosive outflow. So even for the closest massive protostar forming 400 parsecs away, we don't know, which mechanism is occurring, let alone on the other side of the universe. So that is the state of play, and let's see, what else we can say here. Okay, because of this, the time scale is also uncertain. How fast or slow the process is relative to the dynamical times, signal processing time, which is roughly the free fall time for self-gravitating structure. And then the end result, why do we get the IMF, the initial mass function of stars, and why, it's quite, being in a binary or a higher order multiple is quite a common outcome for the process as well. So this characteristic salpeter mass function written in this form is declining the number declining in its mass is m to the minus 2.35 power, maybe with a truncation at around a couple hundred solar masses. Then, how would this sort of star formation process vary with environment in the galaxy or in the high redshift universe? If you're implementing galaxy formation evolution simulations, you need a subgrid model. You always need a subgrid model. So thresholds on density, but perhaps you should consider magnetic fields. And what is the efficiency per local dynamical time of star formation? Okay, here's my outline then. I'll briefly outline observations of the environments. I'll look at ways to test core accretion, and then we'll go to the high redshift universe. Okay, this crazy looking diagram is just mass from 10 solar masses to 10 to the 7 solar masses. And this is just mass per unit area, mass surface density. And in the background here are lines, constant, well, if we have a spherical cloud, let's start somewhere with a spherical cloud, then I can draw a line of constant radius, 1 parsec here, stretching up here, 10 parsecs, 100 parsecs, and so on. And then, of course, I can draw lines of constant volume density. Here's 100 hydrogen nuclei per cubic centimeter equivalent density, and getting denser, 1,000, 10,000, 100,000. And then the free fall time, as you know, scales inversely to the square root of the density. So this is 4 million years, 1 million years, 400,000 years, getting shorter. This is escape speed from the surface of the structure, 10 kilometers a second. In the Milky Way, we've about 10 solar masses per parsec squared on average gas. But most of the star-forming gas is in molecular form. Actually, for CO, we study it with looking at CO molecules quite often. For CO even to exist in the UV radiation field, we need a certain amount of extinction above this line. But most molecular clouds are in these higher mass surface densities, maybe around 100 solar masses per parsec squared, as shown on this axis. 12 CO clouds, 13 CO clouds, sort of denser structures within them. There's still some debate if they're, the importance of gravity. We would say that they are virialized, at least at this scale. there's a range of densities. You've got a higher critical density traces like HCO+, but also the dust emission. So there's dust mixing here, of course. These are millimeter continuum results from the Volcan galactic plane survey. You see structures going up to higher mass surface density, of order 1 gram per centimeter squared. And here are clusters. So the Orion Nebula cluster, its half mass radius is about here, about 1 parsec. It's got a few thousand solar masses on that scale. That's gas and stars. Here's some more clusters.
Can I ask a question?
Yes.
So you have just a cloud. How can you measure mass? I can understand the density, right? But okay, you have the radius as well. What do you assume with the density?
Well, this is under this assumption. So typically we'll measure, I'll show some techniques. We'll typically measure mass per unit area. In fact, that's why we like this axis. We measure mass per unit area either by optically thin.
About the x-axis.
Well, then we need to know the distance and, you know, how big it is in angular size. Yeah. And we can do mass profiles. Yeah. It's the density is generally harder to get at, convert. Okay. Now, actually, so one of the big things we've been working on and others to go after the initial conditions is going after the very early stages of the gas structures, the so-called infrared dark clouds. This is a Spitzer 8 micron image. You see the dark shadow against the diffuse galactic glow. So in fact, this goes to your question. We've developed methods to use the information in this image. It's just 1D radiative transfer through the cloud, but you've got to account for galactic foregrounds. So you can get sort of order arc second scale, full out arc second scale information about the mass structures. That's how we derive the masses of these very dense cores. This is, here you have 200 magnitudes of visual extinction equivalent. So it's very difficult to see any unless you go at long wavelengths. But some of these structures are optically thick at 10 microns. They're optically thick even at 70 microns in the Herschel images. So they're really dense and cold, and these are where we focus our search. So the darkest, the shadows. Okay, so now let's go and test core accretion. So here's this cartoon again, these cores emerging from the clump, time 0 protostar formation. And here, this cartoon, one little thing, as we'll see, massive stars, as they're growing in mass, at some point they can become older than their local Kelvin-Helmholtz time, and then they contract to the main sequence. They become hot, emit ultraviolet photons. They begin to ionize while they're still accreting. So you can have ionized the structures like this. Let's go after the massive prestellar cores first then. So they're threaded by magnetic fields, but also they're turbulent. We mentioned we assume equipetition here. It's effectively like an alpha and Mach number of order unity in the core is the assumption. A core of a given mass, say 60 solar masses, embedded in a clump of 1 gram per centimeter squared, would then have an equilibrium structure, the singular polytropic sphere, that is truncated at about 0.06 parsecs in size. That's about 12,000 AU. If I go to higher pressure environments, raise up sigma clump here, then this would be more compressed, and the starting condition would be denser and would then collapse faster. The internal velocity dispersion for such a core is about 1 kilometer a second, so it's greater than the sound speed. They're turbulent, but some combination of magnetic support as well. If you're interested, the hydrogen number density at the surface of this core is about 1,000 particles per cubic centimeter. So we are, putting some of this physics into numerical simulations. We have heating and cooling functions, PDI-based heating and cooling functions. We follow the chemistry, self-gravity, of course, different strengths of magnetic fields, different initial conditions. We like cloud collisions as a way to compress gas and push it over the edge. So here's an example snapshot of such a simulation. Now, from the low mass community, Paolo Castelli's work has shown that in cold, dense regions, deuteration becomes a very important process. CO is frozen out onto dust grains, and that changes the chemistry. You actually then enhance H2D+, which then donates deuterium to other species. So you build up that N2D+ the deuterated form of N2H plus, high critical density, becomes very abundant. I mean, you can have an abundance of this basically the same as N2H plus, even though deuterium is 100,000 times less. So we go after N2D plus as a way to sort of pick out these cold regions. We're also following that chemistry in the simulations. Then with Cassim student, we're also looking at all the density structures, trying to understand where the massive cores are forming in these kinds of simulations. Is there primordial mass segregation? Does it depend on the field strength? And we look at the structure to infer the field strength, for example. Okay, now observationally, we want to find then these things. So we go up, this is in the Andes. We went, fortunately, ALMA came online in 2013 or so, 2012. And so we just turn ALMA on these infrared dark clouds and look for the N2D plus signature that I just mentioned. And this was in the first cycle of operations of ALMA. There were only 16 antennas or something. And this was our first result, getting N2D plus observations in one region of that infrared dark cloud. Of course, you get a Doppler shift as well, so you have PPV cube, and you can try and find and isolate these structures. So this one in particular is one of our more interesting candidates. That was only about a 1 or 2 arcsecond resolution, 2 arcsecond resolution at the time. This is our mid-infrared based extinction map in the background, up to about 1 gram per centimeter squared, based on the Spitzer 8 micron. This is this C1 South, very deuterated core. So we just go in here and measure the velocity dispersion. We try and estimate the surrounding pressure from this mass surface density map. It is quite round, fortunately, at least in that scale. We just put an aperture down and evaluate things, and measure its mass in 2 ways: dust emission or the extinction map. And in the end, we compare the predicted, basically comparing this virial equilibrium prediction of velocity dispersion to what would be predicted from the model. Now, since then, of course, ALMA's got much better resolution, so we've done surveys of maybe 30 of these RDC clumps at higher resolution, hundreds of these kinds of cores. For the 6 sort of brightest ones, we can compare the observed velocity dispersion to the predicted 1D velocity dispersion assuming virial equilibrium, and get that kind of ratio. So in star formation field, you're reasonably happy. If we look more closely at the more massive ones, we actually see they're subvirial by about a factor of 2. And so we think there is a role for actually stronger magnetic fields in the more massive cores. In fact, we may need them to prevent fragmentation. That's a question, what prevents the fragmentation to give this mass spectrum. Now, following up that example I showed, if we go to higher resolution, we actually see 2 protostellar sources nearby, but this we still claim is separated and isolated in both position and velocity space. And this remains our most massive starless core object. If you look at millimeter continuum, the protostars actually dominate. This thing is very cold and it hardly stands out. So it's very difficult to find these from millimeter continuum alone, but it is booming in N2D plus. There's still debate here. So, people survey, other groups are surveying different regions. Sometimes they find a lack of massive cores, but there are other candidates of around 30 to 50 solar masses. These are the conclusions then. Deuterated species good to find them. So far, moderately subvirial. So we'd have to raise our field strengths up, maybe about a milligauss. Henry Boyther has, it's difficult, but has one of the few polarization studies done of one. They're faint, so it's difficult to do this. We have ALMA accepted proposals in, they've been in for 5 or 6 cycles, never got observed on this region to do C1 South. So this year we'll try again. If you really want to go after the initial mass function of stars, is it set by the core mass function? You really need to go to the pre-stellar core mass function and basically, I think, use this tracer and get dynamical masses. Well, we try, so we actually map, this is an ALMA mosaic, maybe 100 pointings from this region where C1 South is, all across the cloud here. So you see, in fact, all these nice ordered outflows. In fact, they seem to be globally aligned. That's another piece of evidence. Maybe there's some role for large-scale field. We can do millimeter core mass function studies, build up a mass function. We have mass function power law indices here, which are in this unit, saltpeter would be 1.35, so a bit top heavy. But in general, these are really millimeter luminosity function studies. We're seeing protostellar cores essentially, so, and also other groups. So it's not clear exactly. We don't know the temperature structure that well in these things, so the mass estimates are pretty uncertain. So as I was saying, for the pre-stellar core mass functions, we really need to go after the N2D place. Okay, on the larger scale, we are doing several things. To probe this roller magnetic field, we turn the GBT on, and we get large-scale kinematics. So we've got 6 arcsecond resolution of C18O, 13CO. That's shown here. There are ways you could try and infer the magnetic field from the kinematics. We're not sure we believe them, but we're testing them. And then maybe on the last, it was scheduled this last week, I think. I have to check. It was actually observed. We're trying to get the Hawk Plus on this, but we have done several other clouds with Hawk Plus as well. And so we hope to test, basically all of this physics and basically try and determine what is the role of magnetic field also on a larger scale. Okay, let's go to the later stages. Now, in numerical simulations of this process, not from our group, actually from several groups, here's a 100 solar mass core, half a parsec initial rates, only 10 microgauss. It's a pretty weak field, lots of fragmentation. Put in the 1 milligauss field, no fragmentation, no fragmentation. So we're going to go with a single star semi-analytic model in our cartoon based on this kind of work. But of course, you could have disk fragmentation, and we don't have that all built in yet in this cartoon. What we've done is with Yichen Zhang, who's a PhD student in Florida, we have developed a series of models that span this parameter space up to 500 solar mass cores over this kind of range of mass surface density, a grid of models which have two initial parameters, obviously sigma clump and M core. That sets the initial condition. M star is the evolution along the track, what fraction of the mass of the core has gone into the star. And that then sets, at the center here is a protostellar evolution model. So it's a stellar structure calculation with an accretion boundary condition. This is the size of the protostar growing in mass. Here's the main sequence size. This is so protostellar accretion. There's a core deuterium burning. There's a shell deuterium burning. It's a luminosity wave. But as I mentioned earlier, at some point, the star, needs more and more luminosity to support itself and will start contracting down to the main sequence, basically when it's older than its local Kelvin-Helmholtz time, which is decreasing as you go to higher masses. So if I accrete quickly in a high pressure region, this red line, 3 grams per cc, I'm tracking across very fast, high accretion rate, tracking across fast. I land on the main sequence late at a higher mass, could be 50 solar masses. Whereas if I'm in a low pressure environment, I'm creeping slowly, lots of time it's taking, and I've got more time to contract down, and I hit the main sequence, maybe 15 solar masses. So that kind of physics is in here. The properties of these outflows are accretion powered, remember, so they also depend on the accretion rate. So that's also included in the disk wind model in here. Then all that structure is put into a Monte Carlo radiative transfer code. This is the core on the big 20,000 AU scale. So here's the density structure. Here's the outflow cavity. It's wide opening as we go in time. That radiative transfer calculation calculates then the resulting temperature structure. We have the input luminosity from this model. So we got all the heat, the thermal structure, and then the emission properties at various viewing angles. So here's another parameter, the viewing angle of this thing to the outflow axis. I've got 4 parameters and foreground extinction, 5 parameters. That's it, 5 parameters in this model. It's not many for such a model. One thing you notice here is, then you have the spectral energy distributions, of course. We can go to observe systems and try and constrain, sometimes only weakly, the main parameters, the sigma clump. M core, M star in these three projections. That's a simple semi-analytic model. So we are working on testing it with some numerical work. This is Jan Staff's work. So basically, all the same structure here. We, at 100 AU inner boundary, we inject a disk wind that's scaled to the appropriate power of that model. And we can look at, play that again, this is the high density ambient core, this is just the fast flowing outflow. So of course, the real situation is more complicated. But if you look at the opening angle from the semi-analytic to the simulation, yeah, it's reasonable agreement. The opening angle widens up over time. The outflows get more powerful. So one sort of thing you notice here is this morphology change as you track from 2 microns to longer wavelengths. This top outflow cavity is pointing towards you. Short wavelength near light is basically scattering to you. It's dense here. The surface density of the core is similar to that of the clump. With all the dust in here, you can't see the far-facing outflow cavity very well. Until you go to the longer wavelength, well, even at 37 microns, it's asymmetric. More finely symmetric at around 70 microns. So that morphology change motivates the SOMA survey, which again, we started with the beginning of SOFIA operations in 2012. As you may know, then SOFIA is flying a telescope, this what is it, 2.8 unit telescope in the back here. And looks, if you're terrified of flying, you might worry about this big hole in the back of the plane. I was a little terrified of flying, especially in the early days. I came in here looking at all the panels falling off the wall. I mean, you couldn't even get a beer. You couldn't even bring your own beer. And then I turned around and noticed this essential piece of equipment that was this $9.99 Walmart fan blowing furiously into this cupboard here. And they said, "Oh, don't touch that." It's a crucial piece that keeps the thing flying. Anyway, it has been flying. It never crashed. And unfortunately, this last week might be the last week of operations. So here we're using the forecast instrument to do imaging from say 7 microns to 37 microns to really test that morphology that we showed. And here's an example result of this FDSA. So at 8 microns, we have the near-facing outflow cavity. You can see the conical appearance there. As we go to longer wavelengths, you begin to see the far-facing cavity. So in fact, the profile information here, the flux profiles carry information which can really much better constrain these kinds of models. So we've done 50 of those sources, basically 1 per flight, so you get an hour or 2 on time. And the SOMA papers 4 is on the archive, nearly accepted, and 5 will be the clustered regions. So for example, in this parameter space of M star versus sigma clump that we derive, we can now begin to test some theories. In 2008, some people I know quite well proposed what I would say is a kind of crazy theory that to form a massive star, you need to be above 1 gram per cc. And that's a Nature paper, many citations, but what is the physics behind it? The physics is that you need to be in a high pressure region so that you have high accretion rates of lots of low mass stars that heat up the stuff around so the gene's mass is raised up to be massive to prevent fragmentation. Yeah, it seems kind of crazy. Now we have plenty of massive protostars that are on the left-hand side. And we always said, look, I'll prevent fragmentation with magnetic fields. I don't need gene's mass of 100 solar masses. Now we do know, we do notice perhaps a trend that the most massive stars, current mass, M star greater than 25 solar masses here, are in these higher pressure regions. Now our interpretation is that the internal feedback through disk winds, photoevaporation, stellar, all these processes struggle in the higher pressure case. So we put that kind of physics into the semi-analytic model, Tanaka's paper, and we work out what kind of efficiency, star formation efficiency from the core we get as a function of mass surface density. So, for example, in a 100 solar mass core, our model would say or we can actually approach 50% efficiency in a high pressure region. But we've got a 0.1 grams per cc. You know, we're down at 20% here. So if I want to form a 100 solar mass star, well, if I want to form, I don't form a 20 solar mass star out of a 100 solar mass core. So if I wanted to get up to here, I'm going to have even more massive cores. It's probably just rarer, and that could be the reason here. We follow them up with ALMA. So we go after the outflows, hot core traces, various complex molecules start showing up. We're modeling that to process. But this is a very clear bipolar outflow. There's plenty of examples, not just from our group, of very clean, nice, quite symmetric outflows coming from massive cores, high luminosity sources. I think it's unambiguous that in these cases, core accretion is in play here and can try and explain details. So with core accretion, we're working on predicting why is the formaldehyde ice line at 3000 AU and not sort of 6000 AU. That's the level of detail we're at in core accretion models. We wheel out the VLA, we go after the ionized jets that I mentioned. So we've done all of the solar sources with the VLA. We have some kind of synchrotron jet. That I still don't understand. Some massive protostars, I don't know why, have synchrotron emission. So maybe we can chat with some of you later. But lots of them have, we think, photoionized emission, shock ionized emission, and we're actually helping us pinpoint the exact location of the protostar. With ALMA long baseline, you go to roughly 30 milliarc seconds at 1 millimeter. And we can sometimes see binaries, and we get kinematics. This is a 2019 paper, and we can begin to constrain orbits. So there's examples of disk fragmentation, and I'd say relatively ordered binary formation. However, Orion still remains. Its outflow looks nothing like the others, and so there is still a role for interactions in clustered regions. Inevitably, as the cluster density goes up, occasionally we'll have close stellar flybys, which could either trigger an accretion burst or perhaps even have a stellar merger. So this remains an open question, exactly what has happened here. Are there any questions on local massive star formation and how much time? Maybe I have 10 minutes left. Okay, let's push out to high redshift. This is really a separate topic, but as you'll see, there's a connection of the massive star formation physics, but we change a couple of things. So the environments now are more extreme in the sense they're metal-free. This is the result of a numerical simulation of dark matter mini-halo at Redshift 20. The dark matter defines the potential. Gas is hydrogen, helium. There's a little bit of molecular hydrogen that forms in the gas phase that can cool down to about 200 Kelvin. So and as the potential grows and deepens, gas can slowly settle in here. That's where we're going to focus. And the connection we're going to make is to the supermassive black holes, which of course are now imaged and known to be present in most larger galaxies. So we have the dark ages here ended by something, and that's the question, what? We also have high redshift quasars with masses, about 1 billion solar masses inferred. If you are having Eddington limited accretion growth, like saltpeter growth, you can only grow at a certain rate. So you follow these tracks back in time from these redshifts around 7. That tells you maybe what the initial seed mass could have been, depending where you want to form. Because these are so massive, there's not much time here. Your masses can be above 10 to the 4 solar masses. It's been claimed that maybe this is a need for the initial seed mass here to be quite massive, a supermassive scale already, like 100,000 solar masses, rather than a stellar scale around 100 solar masses. What do we know locally? Well, here's a mass distribution of local supermassive black holes. The lowest mass one's around 50,000 solar masses. So what's known is that they tend to be around this mass scale and greater. They're present in most large galaxies. So it's roughly third L star and above will have a supermassive black hole. Come to that in a moment. So there's some galaxies which appear to be lacking. There are limits that go below, quite far below this mass limit. very limited evidence for intermediate mass black holes, be it from the dynamics in globular clusters, ultraluminous X-rays, a handful of ULXs, generally be explained as a beamed emission from low mass black holes or gravitational waves. They had a press release and found an intermediate mass black hole, but it's clearly at this mass scale around 150 or so solar masses. It's clearly part of this population of stellar black holes, merge them together. So there's very limited evidence for say 1,000 solar mass black holes anywhere. Right, so perhaps there's again characteristic seed mass of a 10 to the 5 solar masses, and this is important. How many we need? As we said, roughly all galaxies 3rd L star and above have such a black hole. Then we're this kind of co-moving number density of those sources. What's done in these big simulations, like Illustris here? Well, since we don't know how these things form, they just do the simplest thing. Once a dark matter halo reaches a 7 times 10 to the 10 solar masses, it is seeded and it's put in a seed mass. And that sort of continues. And there's, of course, been some investigation of what happens if we vary the seed mass. Could you grow up from low mass black holes? They're pretty uncertain. So generally don't know what to do. Now, the physics of this process has been discussed for many years. We start with a big gas cloud. It can basically go through, I'd say, 2 main routes. It can fragment into a cluster, and then you try and merge things together again. You probably want to do it before they become neutron stars and black holes. So a limited amount of time. That means you need to have a high enough density, and it means you're also going to make a lot more intermediate mass sources than supermassive sources. From all the work we've done locally, we just don't think these kinds of stellar clusters exist in any sufficient number to be relevant. So most attention for us and other groups focuses on this sort of monolithic collapse of a gas cloud, perhaps through a supermassive star phase. This is where the star formation physics will come in, which then could undergo nuclear burning, end its life with efficient collapse to a black hole, or it could potentially keep accreting and pass the GR instability at around 10 to the 5 solar masses and undergo just a direct collapse. Now, the first place you might look are these first dense structures in the universe in dark matter mini halos. This is this example against redshift 18, hydrogen, helium slowly collecting in the region. Now, we did apply our massive star formation physics in this case. And here's the protostellar evolution calculation, different accretion rates, different cooling, of course, but we still reach the main sequence at around 100 solar masses. It's further along, because the accretion rates are higher, but we still come down here. Your temperature here is 100,000 Kelvin, most energies in the EUV, photoionize. We expected then that we would shut off accretion by disk mode evaporation at about 150 solar masses. This physics is put into radiation hydro simulations by a number of groups, 2 independent groups in Japan. They get a mass function, it's roughly the same scale. This would be not supermassive scales, so-called light seeds. And so most attention in the field for supermassive scales is focused on what's known as direct collapse for much more massive systems. These are now not mini halos, but 10 to the 8 solar mass halos rather than 10 to the 6. They're so-called atomically cooled halos, but they've also got to be metal-free. They've got to be dust-free, metal-free to prevent fragmentation, because you want to form a population of stars. And in fact, you've got to stop that H2 cooling in the gas phase. So you need to be irradiating them with some kind of Lyman-Werner flux from some surrounding source, be it other stars or AGN, which means you've got to predict all this stuff, which is very difficult. Still, they try. There's the distributions of received UV intensity. They try and work out what conditions, how often this kind of condition occurs in the simulation. Very uncertain, I would say. But even these proponents of the theory would find them happening occasionally, but at a low level. So this is the co-moving number density seen in this study. In this WISE 2019 study, Nature, this was even lower. So remember, we need, if we want to make all of them at the start, but it's a tiny little start, but maybe not relevant. So our proposal is we want to make all of the supermassive black holes in a single mechanism. I'm going to go back to the first stars, and we want to explain why there's, this separation of scales here. So 3.1s we define as basically isolated mini halos. So this first thing to form locally in the universe would be 3.1. It has been unaffected by any other astrophysical source. Now, depending what it is itself, it will send out radiation which could affect other things around it. It could also send out metals, but in a smaller region. So a 3.2 is something that's been irradiated, but not polluted. So population is still metal-free. The Brom group have looked at what happens when you irradiate mini halos. You promote free electrons, you actually promote H2 formation, HD formation. You get more lower mass scales. Actually, they predict maybe around 10 solar mass as stars form. If metals have been produced, they'll mix more locally. You start to have population too. Now over here, you see it's far enough away, it's isolated enough that it's another 3.1, undisturbed. Now, why do I care about these undisturbed sources? Well, we need to stop this protostellar evolution track hitting the main sequence. Is there a way we can do it? Well, there is a way, and it involves properties of dark matter. This protostar, this POP 3.1 protostar, the only place in the universe where you have a massive star forming co-located with a dark matter cusp. Could that have an effect? Well, if dark matter is a WIMP, a weakly interacting massive particle, self-annihilates, produces gamma rays, electron-positron pairs, some neutrinos, they escape, but the other energy can support the star. So you can do a MESA calculation with that energy source in there, and you delay the collapse here. This is given some initial WIMPs. If I keep supplying WIMPs in, now here I've got to keep capturing them. So I've got to do a scattering rate off the protons of the WIMPs. If I can keep capturing them enough to supply the energy I need, I can actually stay in this big swollen state. So the argument is, if I can keep supplying the WIMPs at this level, if they self-annihilate, supply energy, I can stay big and cool, very little UV. The gas in the mini halo, which happens to be about 100,000 solar masses, could just efficiently come to the center, and I make a star. That's the argument. So, we were not the first to propose this. Spoglia, Crease, and Gondolo proposed this as having some effect on the structure. We agreed with them later, although I didn't like it when I first heard about this. And then this is Rinaldala's stellar structure calculation. I've gone up to 100,000 solar masses. We're not involved in that. Here, we run with the idea and just say, okay, maybe this is the way. So we put in this physics into a cosmological volume. We basically find the 3.1s in a 60 megaparsec co-moving volume. We have enough resolution to see every mini halo forming, and we just see which ones are isolated. We have one parameter, the isolation distance. Is it, could range from 10 kiloparsecs proper to 300 kiloparsecs proper. First mini halo redshift 40, and then more and more. This point here is this co-moving number density redshift 0. That's sort of what we're aiming at. I guess you could go high and then merge. But we want all of them, so we want to get at least here. We need an isolation distance proper of 100 kiloparsecs. It's all finished by redshift 25, 30, say. That's 3 megaparsecs co-moving at redshift 30. All supermassive black holes in this model are in place by redshift 25. So, when I say that, if somebody has some strong objection, please say it, but that's the proposal. And then with Jasphere, we go down to redshift 0. You see, here's what Illustrious does, this mass threshold. They come very late, relatively late. And in fact, that motivates us. We were in a bar in Stockholm, I think the Churchill Arms, talking to Matt Hayes, and we said, well, how can we test this? Ultra-deep field has a number of galaxies out in this range here. Let's look for AGN variability. Let's go back and reobserve the ultra-deep field. So that was in 2019. In 2020, the proposal went in. Unfortunately, the HST TAC were not in that bar in Stockholm, so they didn't like it. In 2021, they were not in that bar, but in 2022, they were apparently. So in this next year, we will reobserve the ultra-deep field, my first extragalactic observing proposal, and we will look for AGN variability to find just one or two candidates out here can really distinguish the model. So stay tuned. These are just synthetic ultra-deep fields needed for the proposal. Last thing, then I'm done. A physical model for this isolation distance. Could it be the Stromgren sphere from a supermassive star, which puts out 10 to the 53 hydrogen ionizing photons per second in the IgM density at redshift 30? That happens to be about 60 kiloparsecs. Interesting. So here's a model where Stromgren sphere or twice the Stromgren sphere is used as the isolation distance. So here's the first summary just of this part. We know the black holes are present in many galaxies. They have a supermassive scale. They're quite common. Most people look at direct collapse, but it's rare. I've not met any direct collapse person who claims otherwise. We want to do all of them with this novel mechanism involves WIMPs, dark matter. So there's some constraint on dark matter properties. Lots of predictions. They're all in place by redshift, let's say roughly 30. Very unclustered. I didn't have time to show it. They are spread out. So there's differences in the clustering signal. And there'll be differences in binary AGN fractions and gravitational wave rates. So, we are following up on all fronts here. And here's my last conclusion for everything. We're trying to develop a general theory for massive star formation, actually all star formation, really. Also the low mass ones in these kinds of environments. Turbulent and magnetic field core model. So observationally going after deuterated species with ALMA in infrared dark clouds. Later systems, lots of multi-wavelength study really were driven by the SOFIA far infrared forecast camera and then follow up. And then, as we learn more of this physics, we try and apply it in environments we're never really going to see. I think we need something different. There is a physical mechanism that can change the story and lead to a bifurcation of mass scales up to 100,000 solar masses, and it makes clear predictions. So we'll see. Thank you.
So, any questions for Jonathan?
Question. Well, in order for your WIMPs to provide enough energy to their annihilation to support these stars, they have to have, first of all, you need some certain cross-section. Second, you need some constraints on how Caspio is going to be, right? So assuming that they annihilate frequently enough, so both of these constraints are good enough with your purposes. If you work this in all the systems that Fermi has observed, you not see annihilation problem. Dwarf galaxies, center of galaxies. Do you still have enough parameter space for this mechanism?
Yes, we do. We've checked that, of course. A couple of points. The baryons in the mini halo start to dominate the mass inside about half a parsec. They start to deepen the potential themselves, and they drag in. They change the dark matter structure. The gas is very well modeled in simulations as something like a singular polytropic sphere within the density index rho going as r to minus 2.1. And what's seen in the simulations is that the dark matter particles start to follow this. So whether then in the dwarf galaxies you won't have that effect happening, but no, we look of course at these kinds of constraints. What we most care about and what I'm most slightly concerned about is the spin-dependent scattering cross-section. What we've learned is we need to keep capturing the WIMPs as the star is growing. So yeah, we care about the ambient density around, but the star is quite small at this point. It's in high density sea of WIMPs. They're coming in. We've got to capture enough, and actually we've got to refill the loss cones. So that's the process we care about. And the current observational constraints on the spin-dependent scanning cross-section, if they come down another order of magnitude, then, you know, I'll start being a little nervous. But right now, I don't know what, you know, the alternative view pictures, I just don't see any good proposal for making all of the seeds in a predictive way. So I'm, you know, I'm quietly confident about, at least I'm very excited about this, this mechanism. And yeah, we'll see. But of course, we look at the WIMP properties as well. It's a bonus. Constrain the WIMPs, why not?
Just to follow up, because in galaxy formation simulations, do you see a increased range of WIMPs of dark matter particles in larger scales, maybe, that are consistent with what you need to keep accreting?
The simulations have, you know, high resolution simulations have done individual mini halos, which then follow, you know, to stellar densities. At some point they stop and they have to either the sync particle is used. And at this point, yes, one can model the dark matter density. So we've looked at those simulations and we've seen the kind of dark matter densities they have, and that's what sort of normalizes our models.
Oh, sorry. Okay. Yes.
Is it on the screen?
Oh, sorry.
It's about, but not about that matter. But
It's just one at a time, it's fine.
Well, anyway, so just to understand, so you've got the mini halo, it's 10 to the 8. Right?
No, the mini halo is 10 to the 6.
10 to the 6. And this one creates a black hole, which is 10 to the 5.
Via a supermassive star.
Yeah,
Mhm.
right, okay. But this one has to be in the center of the galaxy.
Well, initially it's, well, later it will, you know, so.
How will that happen? I mean, when you say later, because, you know, it's a mini halo and there is another mini halo, the biggest thing. But you want to create just one supermassive black hole.
Right, because there are 3.1s and there are 3.2s. That 3.1 will irradiate things around it. So basically, we need this isolation distance to about 100 kiloparsecs proper, which is 3 megaparsecs at redshift 30. So all those other mini halos, and there are many around, are strongly irradiated. And what is seen from, as I mentioned,
where is the galaxy? That's what I don't understand.
the galaxy will form around this thing. So we have.
I mean, that is just 10 to the 5. It's not going to create gas to create the galaxy, right?
No, all the dark matter, all the mini halos around, and you know, just standard merger histories. Standard merger histories will lead to that formation. I can give you occupation fractions if you want. Let's see if I have the graph here.
So the merger history will not result into merging of this black hole.
We have a few binary mergers. This is a different talk.
Yeah, I mean, somehow you have to change the black hole mass because not only GNR and the 5, but that has to do as well.
Oh, they'll accrete later. Yeah.
Right. Okay. So if you don't have time to go to accretion rate at the redshift of 7,
Well,
that will give you, you know,
if we don't have time, nobody has time.
okay.
Yeah. No, and we do. We have 10 to the 5 solar masses at redshift 30.
And don't you expect then James W, you know, the Univ telescope to actually tell you very, very quickly when they are going to detect, you know, QSOs at the redshift of 10, or perhaps not.
We predict they are. We predict they are. You know, all in place. So the co-moving number density is constant.
So you predict that James WSD is going to see quite a lot of it, right?
That's what we would predict. Yeah.
Okay.
But I have not had time to make detailed. You know, I've got to. I want to. I'm going to start modeling AGN and learn about that. You know, but yes, we'll do that soon.
Okay, thank you.
Actually, hiring people and help.
so there has been quite a bit of discussion about the effect of preheating by X-ray binaries in the period around redshift of 30 or so. So, and the idea is that the mid path of X-ray photons is really long, longer than 2 photons. So So they affect the intergalactic medium, but eventually will form the protogalaxies or may help to accrete the material on your primordial black hole. So how sensitive your results are on the temperature of the intergalactic medium? That's one question. And the other question is, from your theory of collapse, what is the binary fraction that you would expect? Because both of them are relevant.
Which fraction, sorry?
Binarity fraction?
Yes. Well, we haven't made predictions for binarity yet, so that I don't know. But it will be, if they're magnetized to disks, it'll be harder to fragment. So that'll be one question. I mean, we think there's time for magnetic fields to be generated even in the mini halos in the accretion disks. These X-ray photons, from X-ray binaries, but I'd have to predict the progenitors of these X-ray binaries at first, and I'm not sure I'm able to do that.
We have to go really low mass.
But I'd have I have lots of AGN in place. I mean, that they could be the X-ray sources if you like, and let me do it with the AGN.
No, in the sense that AGN, okay, it depends on their mass. If their mass is very high, if the mass of the black hole is very high, then the peak of the spectrum shifts to the UV.
I know, right?
So they don't produce hard enough.
But I'm starting at 100,000 sources. Yeah, they're all there. Lots of X-rays. There's another prediction we just came up with. So I don't need this hard X-ray binary. Give me just the X-rays from the. I should talk to you, find out this evidence of the preheating.
Yeah, I can point you to some words.
Please. Yeah.
Other questions? Hello.
Nice though, thank you. And would like to ask for some reminders from the next simulations. Sorry, did you use this or another approach for feedback?
Well, I showed Illustris, so I'm not involved in that collaboration. For the cosmological volume, for the for finding the mini halos, I didn't have time. Sorry, we just use it's called Pinocchio. It's Pierluigi Monaco's code. It's a Lagrangian perturbation code. It's really like there's only n-body dynamics really, just finding the trajectories of these particles, and it claims, and it's been tested, that it can find, locate dark matter halos and see their mergers. Now we are starting with Ben Keller. Some simulations. I would normally never touch SPH, but he will do an SPH, a simulation of cosmological volume with some of the physics and the dark matter and the gas. Yes, but we've got to start somewhere. So.
Okay. So my question is about the results. So these results in cell functions. This figure where you saw the
yes.
Can you go back?
Mm-hmm. Mm-hmm. Yeah, I can find it.
Okay. Yeah. So all the observations are on the left part of the figure, right? So is there any model that kind of leak this behavior? Okay, I can see that the room was like more than the top feet.
But it's like, it's a good point. I mean, it's like they are doing it on purpose, right? What is there a selection bias in
yes.
observations?
Well, these are the SOMA sources. These are massive protostars, so relatively. So are you saying, why am I missing down here?
Yeah.
Yes. It's okay. You gave an explanation about the points of the figure, but
well, this is what we find in the sample of 50. Now we have done this kind of analysis in infrared dark clouds as well. So we've got another about 100 SEDs to fit. I should put them on this diagram. Maybe I have them somewhere, but I think we also have lower mass stars present down here. In the infrared dark clouds, they're just not part of the SOMA sample.
oh, okay. So there are a few.
Right, but it's that's a good point. We have evolutionary tracks. Well, no, it's a good point. We should. you know, we're just trying to see yeah.
no,
I think you're raising a good point.
Is it a selection bias or is it physics? So, I mean, yeah.
No, I mean, they should exist. And I think they do exist in the infrared dark clouds. And, you know, maybe in a few minutes I can find that.
Okay.
We can check.
Any other questions? No? Then let's stay talking about it. You stop recording? Okay, so there are a few people, okay.